and thank you for coming, all of you. Yes, I'll try to tell you a little bit about what we do at King at the moment. We have a small team, it's only 6 people, but we have built a lot of stuff over the few last years, and we build on top of that. So multiplayer matchmaking is one new use case we try to bring to our games, and it's a proof of concept to some extent. It's something we iterate and try to make better. But I'll try to show you the layers of how it's built, what it's meant to do, and maybe where we are, what kind of next steps. So let's start with some basics. What is matchmaking? It's essentially about trying to find the best experience involving multiple players. You might want to be finding players based on different criteria. In typical games like the typical online shooting games, you care about latency. You want to have best experience by making sure that people can play without any lag. In other games, like in our games in King, latency is less important because players are often matched maybe after a game round or in some other circumstances. So the criteria, how you want to find the optimal players to play together may vary a lot, and the solutions which are used to implement such solutions for these problems may vary as well. So this is one approach on stream I'll be talking about. What are the components of matchmaking? You essentially care about what players are available. You can only match people who actually want to play the game, who want to have the experience. And you need to be constrained by what resources you have. If you have 10 servers which can support 20 games, you can't serve 100. If you have few ongoing games which each need few more players, you can't exceed that resource. So it's one aspect you have to take into account. And then you combine them together. You look at the players, at the resources, and you find the players who should do something at the same time in the system. Why would you use stream? I think that streaming is the natural solution to problems like this. It's a cycle. You collect your players who want to have the experience. You can put them in a window where they wait for some time until the matches are done. You close the window, you calculate who matches with whom, and you continue. It's an eternal cycle. And there's a lot of aspects around it you might want to care about, but the core loop is simple and I think fits streaming very well. Although historically, matchmaking systems were not built with streaming in mind, I think. So I'm hoping that this is a little bit new, what we bring to the gaming world. The other reason why it's streaming is that you get a lot of stuff for free. With technologies like Flink, you get low latency, you get almost infinite scalability, you get fault tolerance, window functions, state, extensibility. It's a lot of stuff which you would typically need to build yourself, which is enormous amount of work. And that's why Flink and Squirrels are great, I think, fit for these problems. But you need more. The core technology is great, but you need more things to actually deliver a system for gaming customers. You may need to care about real-time metrics. You need to know what's happening in the system. What's my latency? Are any players getting stuck? Am I serving the data I'm supposed to? You need A/B testing. You need to verify that the algorithms you bring into games are the right ones, that they are the most optimal ones, and you want to iterate this problem to get to the best possible experience. You may want to simulate. You may want to look at the new algorithm and see how would it perform on past data. You may need machine learning, artificial intelligence to aid you in those use cases. You want to change things dynamically, so you don't have to stop everything, deploy from scratch, and have a lag on the game when people don't get matched. You may want to talk to clients, you want global state. There's a lot of things which can be built on top of Flink, but are not there by default. So that's where our effort inside King comes into place. We are building a system we call RBEA. It stands for Rule-Based Event Aggregator, but that's just something we named many years ago. It has evolved quite a lot since. And what we are now building on top of it is an extension for matchmaking. It helps us to do dynamic scoring, create windows for particular matching, to reactions when a match is found, sending requests into the pipeline, which actually starts the process. A lot of small things around it. It wasn't actually much work. It's really a small extension, but it seems to be quite powerful and is already on the way towards some of the biggest games we have. So what is RBEA? How does this system work? What is it good for? At the heart of it is, of course, data. The data we receive at King is coming from our games, sometimes some other sources, but it's a lot of information coming in all the time. I'll talk a bit more about what events we get, but it's high volume. It's over 100 billion events every day, peaking quite high as well. And all of this information is streamed into our RBEA platform. RBEA is built on top of Flink. We have a fixed pipeline into which we are able to dynamically deploy new logic, new scripts. There were some talks earlier on, which describes something a little bit similar. Maybe there's multiple companies taking similar approach to have a kind of static pipeline of a job, which you can dynamically modify as you need. But with RBEA, which we use for a lot of use cases, the core thing is that you can just put in more scripts as you need and do new magic with it. Key thing is that it's very stateful. We remember a lot of things about our players, which helps us to drive the right content to them, to do the right thing at the right time, because each event in isolation is just a piece of information. You only get context if you look at what events precede it. And for that, what we use is called user state, and we dynamically calculate on every incoming event. One thing we do is machine learning. We have integration with TensorFlow serving, and I think that teams are looking into using the TensorFlow transformation as well, what was just mentioned on the previous talk, and that helps us to make predictions. It's again, the system is built in such a way that what you do on training, the inputs you put into the system are the same as you do on real time, because as was mentioned earlier, if the inputs differ, your models will stop working. So we try to create environment which will support anything what our AI teams actually need. And on top of this, like raw technology built on top of Flink, we provide a lot of layers which help our end users, game teams, finance teams, data scientists, to use it in the most efficient way. We provide APIs, we provide UIs, and we build products which just use RBEA underneath, but hide otherwise whatever happens. So we create dashboarding tools, things for funnels, for triggering dynamic actions on incoming events, and things like that. The main use case is analytics, so we can see what's happening in real time or what happened in the past and reprocess. We use this system for personalization to drive content which is for individuals, which isn't on some segment, but for one particular person. And more, we try to put game features on the system, allowing us to just power features inside our mobile games, which from end users' perspective, from the players, don't look like there's any technology involved, but actually there's a lot of stuff going behind the scenes which help us deliver the best experience at the right time. Also use cases, predictions on machine learning, which can power different things in different places. But in here, I want to talk mostly about the multiplayer matchmaking. Still to mention is that this system can work both on stream and on batch, just like many others, which is useful for a bunch of things. To talk a little bit more about the events which power the system. So they come from the client devices, are sent over our SDK, bridged over public internet on our servers, where they may get enriched with A/B testing data to help us drive, again, different experience to each player and measure how they differ, what is more useful, what is less useful. And ultimately, over Kafka, they end up in our platform. The events are varied. There's over almost 3,000 types of events at this point, and they can be related to things like game mechanics, gameplay itself, like how many red candies you may have crushed on a level, about social graphs, A/B testing, messaging. The user state is still something I would like to stop at, because for multiplayer matchmaking, state is really paramount. You want to know as much as you can about the players to be able to find the right matches. And user state is essentially information about the player's past behavior. As I mentioned, if you have one event with piece of data, it only makes sense if you know what events precede it. And state is a condensed form which contains data which you really care about. In RBEA, we have both standard state, which is shared for all scripts, which everybody gets for free out of the box. And you can create your own state for particular script as you go. State can contain many things. It can be what build version you are currently using on the client, how frequently was user active, what's user's latency. Essentially anything we send from client to the server side can end up in state in case it's useful for some system downstream. Now, if we look into the actual matchmaking, how does it work? So as we mentioned, there are events coming into the system all the time, and game teams may decide that, all right, I want to send an event called my special matchmaking feature start. We know that if such event arrives, we can dynamically react to it. Game team would develop a script, a piece of logic which says, in case I'm getting this super duper matchmaking start event, I want to react to it and do something useful. When this event arrives, it has access to the user state, so we know who's the player asking for the match. what level this player is on, what device player is using, a lot of data. And we also know what A/B test is user part of. So we can, again, drive experience a little bit differently, depending on who the player actually is. Once we have this information, we calculate a segment. Segment is information which tells the system that if user is in a different segment than any other, they can't be matched together. An example could be that, for example, if there would be a law in some country that in this particular country you can't match players from another countries, you could say that there's a special segment for that country and everybody else is in the other segment, and they will never mix with each other. It's used for A/B testing as well, because with this we can enforce that people from different A/B tests don't interleave, that they will not be affected by one another. The other piece of data we are sending over is proximity vector. We want to capture how can one person relate to another, how far they are from each other. Mathematically, these things are very simple. It's just you calculate proximity on two vectors. There's no special magic, at least in the default implementation we have at the moment. But the vector can be calculated from a lot of data, which makes it interesting because of the state we have. So once you have these two things, what we create is we make a global window where every player who currently activates with this super duper matchmaking event creates a segment and vector, is put into a global window, which is unique for that particular segment. And we run an algorithm on that window. The window is closed every second. It's configurable, but you can say how often you want to calculate what are the pairs or what are the matches on that window. It can also flush or close when you reach some amount of players. So let's say that you might have 10,000 players starting a game every 10 seconds. So you might want to say that if the window has more than 10,000 users, you want to close it right away. It's something Flink supports, it's quite easy. And when the window closes, you make the calculation. There's some flexibility in it because the matching script which game teams create can advise the window how it should perform, what matches to find, how many players, what's the expiration of a request. So if you can't find a match, when you should still keep the user in the queue, in the window, when it should be sent away and just notify that there's no match for you. We are sorry, but there's nobody to play with. There's some logic around it, which game teams need. And we also plan to add the concept of resource availability. So you would have a site input into the windows, which would be advising them on what is the availability of resources to power the system. Once you find the matches, the output is two pieces of information. You either find some matches which you react to, or some people just expire that they didn't find a match in a particular amount of time. Then there's a reaction script. So you say, all right, we found these 10 players who are close to each other based on whatever algorithm and proximity you specified. They should do something. We should activate experience, which can be done in different ways. We can notify game server. We can start a task on the client side. We can just log it if the process runs in some troubleshooting mode. What's important is that all of these things can be tracked, so we can send events for measuring, and they power, again, the whole RBEA system, so we can make real-time aggregations, visualizations on how things perform, essentially for free, out of the box, with no changes needed, which will be powerful, because that's something we would otherwise have to build again. The system also allows us to do simulations. We can replay past data and see how the data would be applied on particular configuration, what matches will be found, and help us to make a better game in the end. I have a small example of a very, very simple script which shows some of the concepts. So in this example, at the top, we tell that on every start of a game, in this case, the event, the trigger would be a game start event. We say that we want to create a match type called body match. We want to find 2 players, and we are creating segment on client platform, meaning we would not be matching players from iOS, Android, Windows together. They would all be in separate places, isolated from each other. And we tell that users should be ranked on proximity based on their highest level. So if your highest level is close to somebody else's, you are more likely to be matched with that person than if you are on a farther away level. It's just an example. It's not something we really run, but to demonstrate. So with this data, with the segment and vector, you simply send data to the engine, which starts the window, does the 1 second periodic flushing, makes the calculation, sends the output, in this case, to default output on Kafka, which could be reacted to. And the builder The match type builder at the top is something we can iterate to add more algorithms, add more properties, add more functionality. So ultimately, game teams can write a script, tell exactly what they want, tell what features they want to run in their game, because they can deploy 20 scripts simultaneously for different parts of the game. And we just make sure that this runs and produces data they need to power their use cases. It's quite neat. Game seems to love it. Let's see where it goes. And that's what I wanted to share with you today.
Okay, so we have some time for questions. Are there? Yeah.
So I assume once the matchmaking has occurred, the match is played, and then how do you evaluate then how good your matchmaking was, like after the game has been played? Like what metrics would you use there? Because in some way you got to like evaluate, like, right, how well did I do, right?
So in King we have an extensive A/B testing tool and A/B testing processes which allow us to measure different experiences against each other. We look at the various metrics across games which can tell us if some particular feature or twist on a game is working or not. So then this system is hooked to the same techniques and allows us to measure like how happy the players ultimately are by having this experience versus some other one.
Hey, there's one thing I might not understand. Usually in streams like that, data is sharded, partitioned, for example, by user ID, right? It might be in your case as well. If it is, then you, in a single process, you actually don't have data about, I mean, when you have a user A, you probably don't have data of user B that you would like to match with. Do you solve this problem somehow?
With the global windows. So by global window, you actually put players across different partitions into one place where they mix and match together.
Ah, so your process actually is not parallel.
It is parallel on calculating states and the proximity vector and the segment. But then inside the window, the data is in one place where they can be matched against each other. And because it's a real-time system and there's not like millions of players starting every second, even on like largest 2 games in the world, the data volumes of the actual window are never super large. They are quite constrained.
All right. Thank you very much.
If you need to keep counters or features on users, do you keep them, if it's a counter since the beginning of time, you need to maintain this counter forever? I mean, so your state is forever? I mean,
our state is large, yes. We eventually could drop it at some point. We could introduce some expirations, but if a script is live, deployed, and keeps on calculating, the state will not go away. Also, the global state we keep for all scripts centrally is there forever. So the states are actually very large. But Flink helps in that. It's not a problem. With RocksDB, with some SSD drives, enough parallelism, you can handle tens of terabytes without too much trouble.
Any other questions?
Do you use machine learning on Flink? Because you said that there, in some part, you use it, and
So
where?
In RBEA, as a feature, we have a possibility to invoke a TensorFlow serving model. So your script can tell, now I can calculate my feature set, some array of doubles, and you can asynchronously send it to TensorFlow serving and react to the response it gives you.
Okay, thank you.
And Yola is the guy who implemented these things, so he might also give some more insights into it. At least that part for sure.
Okay, is there any other questions or? All right, so thank you very much, Vladimír, for that.
Thank you, guys.